Hi everyone, just addressing your feedback from today's lecture on molecular geometry and the shapes of molecules and VSEPR theory. Um, I'm a little confused about determining VSEPR geometries still. How do valence electrons play a role in it? Just sort of like fundamentally, the idea of VSEPR theory is we're trying to find, or we're trying to predict the best arrangement of atoms in a molecule, how the atoms would like to naturally arrange themselves in three-dimensional space. And essentially what you're trying to do is figure out the optimum geometry, the one which is lowest in energy, the one that minimizes stress, minimizes repulsive forces. So when you're dealing with a molecule, you have a bunch of charged species. And the charged species that you're dealing with are primarily electrons. The electrons can spread out, they are taking part in bonding, they're moving all over the molecule, but generally they do want to repel themselves in some respect. So the very basic, that's sort of the basic idea of VSEPR theory, is just trying to predict what is that optimum arrangement that minimizes the interactions, that takes charged particles and moves them as far away from each other as possible. That's what VSEPR theory is all about. Now, how do valence electrons take a role in that? Well, the valence electrons are the ones which are taking part in bonding. They're the ones that spread out. Those are the ones that take up the most space. And since they are taking up the most space, they're going to interact with each other the most. So forces are interactions. In VSEPR theory, or the idea of VSEPR theory, is you're trying to minimize those interactions by taking your electrons, your valence electrons, and move them as far away from each other as possible. So those valence electrons might either be in bonding pairs or in lone pairs, and VSEPR theory and all the VSEPR geometries and formulas are trying to figure out what is, for a particular combination of bonding pairs and lone pairs, what's the optimum geometry. So there is a whole set of theory, and there's calculus to sort of go through and predict the bond angles for a certain number of configuration, for a certain number of attachments or species to optimize. But we don't expect you to do any of those calculations. We expect you just to look at the solutions or know the solutions, which are all of the VSEPR geometries and associated bond angles. Which gets me to the next question: do we need to memorize all the geometries? If so, is there an easy way to do that? Yes, essentially you are going to need to memorize all of the geometries, and for this class I'll just go ahead and say yes, you have to memorize all of them. In practice, I'll tell you that you won't use the majority of them. I mean, as you go on, you'll see, again, I'm trying to think of the classes, that the chemistry courses that you'll most likely take are organic chemistry and biochemistry. And in organic chemistry, you're dealing with carbon, hydrogen, nitrogen, and oxygen. Those are rarely going to go. Oh, do I have that with a copy of? Carbon, oxygen, and hydrogen and nitrogen, they don't violate the octet rule. So they're never going to have more than 8 electrons around them. And since each of those electrons can exist in bonding pairs or lone pairs, you're rarely going to ever have more than 4 attachments. Sorry, I wanted to reference the... where did I put that? Ah, here we go. You're rarely ever going to have more than 4... Here we are. You're rarely going to ever have more than 4 attachments for the molecules that you'll experience in organic chemistry. So in practice, you really need to know tetrahedral, trigonal planar, and anything derived, and linear, and anything derived from those. So that's where you get trigonal pyramidal. If you have one lone pair, you have a tetrahedral geometry, and you replace, if you have a tetrahedral geometry and you replace one of these with a lone pair, you go from a tetrahedral geometry to a trigonal pyramidal geometry. It's still a trigonal because there's 1, 2, I can't see this, 3 attachments, and they do form a little triangle, but instead of all being in the same plane, where should I show you this? Instead of them all being in the same plastic. Sorry, I just want to get my model kit together here. Okay, so for example, this would be a trigonal planar geometry because there are 3 attachments, but they are all lying in the same plane. They're basically flat. This would be a trigonal pyramidal because there are 3 attachments, but they are not flat. They are not all in the same plane. They're pointing down. So something like ammonia tends to make trigonal pyramidal structures. Those are the types of structures that you'll need to not so much memorize, but those are the ones that you will end up using the most as you go through organic chemistry. And in biochemistry, again, biochemistry is mostly dealing with organic molecules. You do see a few transition metals if you're looking at, you know, lots of proteins do end up having a few heavy metals in them. So you will use a few of these other geometries, but mostly it's the first 4. But I will tell you that you do need to memorize all of them. Is there an easy way to do it? There's not really any good mnemonics that I've found. I've found the best way to memorize them is attach the numbers and the names and the shapes to an actual physical geometry. So either working with a model kit, spend time looking at the model kit, looking at the shape and noticing, that is a fairly distinctive shape. What is the name of that shape? I'm not used to looking at things that have this particular shape. Spend time thinking about it visually and structure and 3-dimensionally. So either best way to do that is with a model kit. Model kits are expensive. There is an online simulation which I will post a link to, which does I think, an excellent job of visualizing these, especially in the context of VSEPR theory. So I will ask people to look at that. Why do we need VSEPR theory? Will we do any calculations with it? You won't do any calculations with it. All the calculations have been done for you, so to speak, to figure out the geometries. Why do we need VSEPR theory? It's not so much that we need it, but we make use of it to explain why molecules have the shape that they do. The most important thing to come away from here is that molecules do have a very particular shape. They have a very particular arrangement that is how's the word like that? Idiosyncratic? That's not the right word I'm looking for. They have particular geometries, particular shapes, and details of that shapes will affect their chemical reactivity. So I gave an example of that today with cisplatin, that you can make a small change of the geometric arrangement of the atoms. Same atoms still attached to the same molecule, but the geometry has been changed a little bit. So that's one example of where molecular geometry comes into play, and your first foray into understanding molecular geometry is just getting a baseline knowledge of all the geometries. VSEPR theory is a way to explain why these geometries occur. So why do you need it? We use it to explain where all these different shapes come from and how you can predict the shape of a molecule just by its basic arrangement of electron pairs and lone pairs. How do you determine geometries if there are resonance structures? So if you have resonance structures, so I guess I worked through an example of that earlier today. When you have resonance structure for something like nitrate, I'll just leave this off here. So the nitrate ion, something simple like the nitrate ion, yeah, this should have resonance because all of the bonds can they can shift between being double and single bonds. So really, you should have a structure that looks something like this. But at the end of the day, you still have a nitrogen attached to 3 distinct atoms. So I would have X, 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 and my central atom here I'll call A, so this would be AX3. So whether I count these as actual single bonds or actual double bonds or not, VSEPR theory doesn't care whether they're single, double, or triple bonds. It still just treats them as a collection of charges that take up space and whose and you're just basically trying to get those collections of electrons, those collection of charges, as far away from each other as possible. So VSEPR theory doesn't care whether they're double or single bonds. So as far as resonance is concerned, you don't need to worry about that. Resonance can be there can be some difficulty, or not difficulty. There can be some complication when you're dealing with resonance involving lone pairs. But those are somewhat few and I won't say they're few and far between, but in those cases, VSEPR theory probably isn't the appropriate theory to utilize to predict the shapes. To do that, you need a better understanding of chemical bonding in terms of valence bond theory, and we will discuss valence bond theory next week. So for the time being, I will just say you won't have to concern yourselves too much about resonance and VSEPR theory, because yeah, VSEPR doesn't have too much to say about about resonance. Or it becomes limited when you need to take into account resonance. So again, resonance was something that we tacked on to Lewis theory, because Lewis theory is a relatively simple model of chemical bonding. Chemical bonds are complex, and they don't exist as static single and double bonds. Really, the electrons are allowed to freely move throughout the molecule, and so it's a little bit more complicated than that, and you need a higher level of theory to explain it. And VSEPR theory is also a relatively low level of theory for predicting molecular geometry. So when it comes to the problem of resonance, there's not too much you can say about it in terms of VSEPR theory, but we'll come to that in a little bit more detail next week. Does the octet rule still apply in this section? Yes, octet rule still definitely applies. We're using the octet rule to predict Lewis structures, and if you're trying to predict the shape of a molecule just from its chemical formula, you would need to know basically its basic arrangement of electron pairs, and the best way to do that is with Lewis theory, or the Lewis model. The Lewis model says you should be following the octet rule unless you're from the third period and down, or you're dealing with atoms in the third period and down. The difference between BF3 and NO2- in terms of angles and strength of repulsion was somewhat confusing. Okay, fair enough. Let me try re-explaining that really quickly. So something like BF3 I guess I'm just going to kind of expound upon this idea. So this is the nitrite ion. And I would say that these both have, if you were going to ask me to identify their shapes, so let's identify their molecular geometries. So the VSEPR formula for BF3 is, okay, around the central atom, I have three other atoms. So its VSEPR formula is AX3, and that would classify it as trigonal planar. This one, around the central atom, I have two other atoms, and I have a lone pair of electrons. So its VSEPR formula is going to be AX2E, which would classify it as bent or angular. It's called bent because it would have two attachments to it, two atoms attached to it, and so you might naturally try to draw it like this, which would make it look like it's going to be linear. It's going to have there's just going to be a straight line, 180 degrees. But the idea is then you tack on a lone pair of electrons, and those lone pair of electrons repel the electrons in these bonds and bends them down from a linear form into a bent form. Hence why it's called bent. Now, in terms of VSEPR theory and predicting things, I would say that these guys have the same basic geometry, or sometimes I would say they have the same electron group geometry, in the sense that they do have three regions of electron density around the central atom. 1, 2, 3, 1, 2, 3, where the third one here for the nitrite ion is this lone pair. So they both have the same steric number, so that's the main column down here. Steric number is just the number of things around your central atom. They have the same steric number of 3, but meaning that they have three attachments, but the types, the nature of those attachments is slightly different. For the nitrite ion, you've got a lone pair and 2 atoms. For BF3, you have 3 atoms. All 3 of your attachments are atoms. So there are some similarities, but yeah, they do have different molecular geometries. We would say they have the same basic geometry, though, as far as VSEPR theory is concerned. The visual rope example helped, but once we started writing on the board again, I got confused. Fair enough, and I think that might actually just be on me, because I think maybe this would have been, probably would have been a little bit more helpful if I crafted some of these examples maybe as a worksheet, where people could have basically they could look through the algorithm. I don't think I portrayed the algorithm necessarily as neatly as I could, so that's on me. But we will get more practice. You'll have plenty of time before you are finally assessed on it. I'm going to be writing up and posting the homework assignments. So you'll get some practice through the homework. I'll be available for office hours. We're going to do more practice involving predicting geometry and applying VSEPR theory in subsequent classes, subsequent lectures, so we will get more chances to go over that. So hopefully that will end up clearing up the confusion, and I will try to take that into account as I'm planning out subsequent lectures. I'm confused on how the bond angle for tetrahedral is 109. So the idea is, and I think I jumped through this main idea a little bit quickly with my demonstration. My demonstration has the way people naturally arrange when I had 4 attachments. So imagine this is 1, this is 2, this is 3, and this is 4. So if you have 4 things attached, and right around my knuckle here will be the center. If you have 4 things attached, if you're stuck in one plane, for tetrahedral you have a steric number of 4. So you imagine that, okay, there should be the optimum bond angle for 4 things is 90 degrees. But that's not actually true, because the molecule is not restricted to lie in a single plane. Things can move forward, or move, for me that's forward. Things can move backwards, or things can move forwards. And so things don't have to be flat, they can form kind of a little bit of a bent shape. So instead of being, if you can look at this without perspective, it looks like you'll have a cross here, but in actuality, they are not flat, they are bent around. So they don't necessarily need to be at 90 degrees. They can bend out of the plane a little bit, and their bond angles can increase from 90 degrees to a little bit more, 109.5 degrees. So I apologize. I had a giant protractor where I was actually going to measure the bond angles, and I'm kicking myself for leaving it at home today. But maybe I'll try to get that right next time. I don't understand what is an axial or what equatorial is. So that's something that I put also on the sheet here. This is particular for the trigonal bipyramidal base structure when you have 5 attachments. So the trigonal bipyramidal structure looks something like this. And essentially, it's called trigonal bipyramidal because if you look at the basic structure, there is a trigonal planar shape here. And then you come in, not with, because again, this is has a steric number of 5, so there should be 5 attachments. If you look at the basic, there's 3 attachments, and then you come in at the top and bottom with 2 others. So you come in one from the top, and you come in one from the bottom, and you get something that looks like this. So the idea is that we call the ones that come in at the top and the bottom, we call those axial positions, because sort of like a globe, it rotates around its central axis. And then we call the ones around it, the 3 that were around the ring initially in the original triangle, we call those equatorial positions. So again, I kind of like to think about this as sort of like a globe or the Earth, where you have an equator that wraps around Those are these positions. We call them equatorial, and the ones on top we call them axial. And those are just two extra names which are thrown out specifically for the trigonal bipyramidal geometry, simply because it doesn't have the same type of symmetry as all the other ones. All the other geometries have some type of internal symmetry where you don't need to specify, oh, this is one particular position, this is another particular position. All positions are essentially equivalent. So, for example, if I was going to do methane here, so let me show you a methane molecule. This would be like a methane molecule, and I'm just trying to specify that whether I'm looking at a hydrogen here, or a hydrogen here, or a hydrogen here, all of these positions are essentially identical. There's tetrahedral symmetry, or there's four-way symmetry around every single one of these. No individual placement or no one bond angle is larger or smaller than the other. That's not true in the trigonal bipyramidal model. Between these two atoms, there's a 90-degree angle, and between these two atoms, there's 120 degrees. So in a trigonal bipyramidal structure, VSEPR geometry, you can make a distinction between axial positions and equatorial positions. And those terms will pop up again a little bit when you get to organic chemistry and you're looking at cyclic structures or hexagonal. Well, I won't expound on it too much. Anyway, I'm not going to stress that too much. It's something to be aware of. But it was not within my current learning objectives for the lesson for today. So I hope that addresses all of your questions and concerns. I will see everybody either during lab today or tomorrow, or if not, I'll see everybody on lecture on Wednesday. See you.